Welcome back. In today's lecture, that is in part 8 of Electrostatics and Coulomb's law, I will be covering some theory part on electric field and its correlation with gravitational field, and what are electric field lines and their properties. What is electric field? And let's say before doing electric field, can you tell me what is gravitational field? You have already studied gravitation in your lower classes. Can you tell me what is gravitation? Gravitational field, sorry. Gravitational field, for example, we have got Earth over here, and if I place something over here, it feels an attraction for Earth. That means that this region is that region where if I keep something that experiences the effect of Earth. For example, if I place this pen over here and it is simply drop it, it falls down because it is feeling attraction for due to Earth's gravitational field. So all this space around Earth where its effect can be felt is gravitational field of Earth. Similarly, if I keep a charge over here and another charge is placed somewhere in its vicinity, it experiences a force of repulsion or force of attraction depending upon whether they are of same polarity or of different polarity. So that region around a given charge where its effect can be felt is electric field of that charge. The electric field practically extends up to infinity, theoretically extends up to infinity, because the force is proportional to 1 by r square as per Coulomb's law. That means that F would be 0 if r is infinity. That means even if I keep it at quite far off place, even then it will experience some force, no matter how small that may be. That means that the field over here is weaker, field over here is stronger, but everywhere the gravitational field of Earth is extending throughout into the space up to infinity. The electric field has the same property. The electric forces also follow inverse square law, just like gravitational forces. This was gravitational, this is electric. The electric forces also follow inverse square law, just like gravitational forces. So that means that even if I keep this charge quite far away from the given charge, it will still experience some force, however small that may be. That means that whether it's gravitational field or the Coulombian field, that extends up to infinity. So, but obviously at far off distances it will be really weak to be of any practical importance. Excuse me. So, to tell you about the strength of electric field, we use a parameter called electric field intensity. Now, electric field intensity is a mathematical parameter which gives you the strength of the field, whether the field is strong or the field is weak. So, electric field intensity is given as force experienced per unit test charge. As just by looking around in this empty space, I cannot tell you whether the gravitational field of Earth exists or not. I will have to keep something to see if it experiences a force or not. This is, in this case, is test mass. Just to test the gravitational field, we put a test mass. Similarly, to test whether the electric field exists around a place in some region, I'll have to put a small test charge. Let's say that test charge is Q0. This test charge, by convention, is always taken to be positive. That means electric field is basically force experienced per unit test mass, but this test mass must be infinitesimally small. That is, I should write it down mathematically as electric field is limit Q naught tending to 0 F over Q naught. This limit is of extreme importance because if I keep that test charge to be bigger, then it will have its own electric field. Then what you would measure would not be the electric field of this particular charge only. That would be the probably vector sum of individual fields produced by one charge and the test charge itself. So we assume that test charge is very small, so small that it's tending to 0. We know it is not possible. Because of quantization of charge, we know that the smallest possible charge which we can have can be an electronic charge. You cannot have charge less than, a charge on the body less than the charge on an electron. Though that means if you want to measure electric field of an electron, you will have to put another electron to measure its electric field. Now this is not right because the limit is not being satisfied. The limit would be satisfied if Q naught is very small in comparison to the charge due to which you wish to find out the electric field. Now this is a very trivial situation. However, practically it can be solved really easily because we don't actually measure the electric field of one electron by keeping another electron near to it. We do it theoretically. So we need not to worry much about that, but we should know at least theoretically there is a trivial situation existing over here when we say that limit Q naught tending to 0. Keeping this aside, this is the general formula for electric field now. What is electric field of a charge? It will be given as limit Q naught tending to 0 F over Q naught, where Q naught is the test charge due to which has been placed there just to see the existence of the field. Now there are two terms over here, the electric field and electric field intensity. Electric field simply refers to region or space where the effect of the charge can be felt. But electric field intensity is that mathematical parameter which will give you the strength of the electric field. However, quite often we use these two parameters for each other without consideration. So normally when we say electric field, we normally refer to electric field intensity. Don't get confused over that. Over next many lectures, you would find, especially when I will be covering electric potential, the concept of potential can be very well understood if we understand the gravitational potential. First, both gravitational forces and electric forces are conservative in nature, central in nature, and both follow inverse square law, and their laws are quite identical. The concept of gravitational potential is quite intuitively known to us. For example, if I keep a water tank on top of the roof, the water automatically flows down. Now everyone knows this. So that means that when I keep a water tank on the top of the roof, that is at high potential and water is flowing down to the ground to the lower potential. Similarly, when there will be two charges and if I place another charge somewhere, that charge will move in the direction of decreasing potential. I'll use this analogy very often between gravitational potentials and electric potentials because the gravitational potentials are intuitively known to us and electric potential will draw parallels from that. So don't get confused when I repeatedly doing numericals or concepts on electric field. I will be using the concept of gravitational field, electric potential, and I will be using the concepts of gravitational potential. Don't get confused over that. That will be really helpful for you. Anyways, now let's come back to the mathematical expression. The electric field intensity, which I told you that I'll very often be calling it simply as electric field, is given as limit Q naught tending to 0. It is force experienced by the test charge per unit test charge. Let's write down the expression for, if I see only the magnitude of electric field. I'll go to the concept of direction a little later. Limit F. Now I've got charge Q and I wish to find out electric field at a point P, which is at a distance, let's say, R away from it. Whenever I wish to find out electric field at any point, what I will do, I will put a test charge from my side at that point. If it's a plus charge, it will repel this test charge Q naught with a force F. That F, the magnitude of that F is 1 by 4 pi epsilon naught Q naught divided by R square, simply Coulomb's law. You are very much familiar with this expression now. Divided by this Q naught. This Q naught gets cancelled out, and if there is no Q naught in the expression, there is no fun in writing down the limit. So simple expression for electric field turns out to be 1 by 4 pi epsilon naught Q divided by R square. The units of electric field are Newton per Coulomb. Units of electric field are Newton per Coulomb. This is the SI unit of electric field. Can you give me the CGS unit for this electric field? Need not to tell you, that will be dyne per stat coulomb. Dyne per stat coulomb. But how many dyne per stat coulomb are there in 1 Newton per Coulomb? You can pause the video and calculate it and then see if you are correct or not. You can pause it right now. Okay, if you have come back, let me calculate it for you. 1 Newton per Coulomb. 1 Newton can be written as 10 raised to the power 5 dynes divided by 1 Coulomb is, 3 into 10 raised to the power 9 stat coulombs. This turns out to be 1 by 3 into 10 raised to the power minus 4 dynes per stat coulombs. This is approximately 0.33 into 10 raised to the power minus 4 dyne per stat coulomb. Did you notice one thing? Did you notice one thing? The CGS unit of electric field is bigger in magnitude than the SI unit. Anyways, let's move further. Now, the electric field is represented by something called electric field lines. Let's go to what are electric field lines and how charges interact and how we can find out the properties of these lines. Assume a plus charge, positive charge, placed at some point in space. If I place a small positive test charge, need not to tell you that it is a positive test charge, because I have already told you that by convention the test charge is always taken as positive. Now if I keep a plus Q naught charge over here, what this positive charge will do? It will repel it in this direction. If I keep this plus charge over here, it will repel it in this direction, similarly in this direction, similarly in this direction, and so on. So there are a number of lines coming out of this positive charge. These lines can be termed as electric field lines, or lines of force. And you can see that a positive charge is acting as a fountainhead of these electric lines. The electric lines, they just diverge out of the positive charge. Had there been a negative charge over here, if I place a negative charge, the positive charge will tend to come towards it. The test charge will tend to come towards it. You can say that a negative charge acts as a sinkhole. As you put water anywhere in the sink, it all goes to the sink. It converges towards the sinkhole. Similarly, all the electric lines, they tend to converge towards the sinkhole. This is called positive divergence and this is called negative divergence. Those students who are familiar with Punjabi, I can say that ਲਾਈਨਾਂ ਇੱਥੋਂ ਖਿਲਰਦੀਆਂ ਤੇ ਇੱਥੇ ਇਕੱਠੀਆਂ ਹੋ ਰਹੀਆਂ, ਖਿਲਰਨ ਨੂੰ ਹੀ ਡਾਈਵਰਜੈਂਸ ਕਹਿੰਦੇ ਆ। So lines are diverging out of this positive charge and they are converging towards this negative charge. So what are electric lines? Electric lines are merely representing the path along which this test charge, positive test charge, will move if it is free to move. If you put it somewhere and moves in a particular direction, that path along which it moves is termed as electric field. Very stupidly, many people, they'll say this is how the positive and negative, this is the mechanism of interaction. No, this is not the mechanism of interaction. Mechanism of interaction between two charges is through photon exchange, and that's a separate topic, exchange force theory. Sometime later I may come to that, but I have seen many people using this stupid statement that this is the mechanism by which the positive and negative charge interact, or any two charges interact. This is stupid. Don't say this thing, please. They are merely hypothetical paths drawn around positive and negative charges, along which a positive charge, along which a positive test charge will move if it is free to move. So that's the definition of electric field line, or force field lines, or line of force, whatever you call them. So what are electric field lines? They are the paths along which a unit positive test charge will move if it is free to move. That's all. Now what are its properties? I have already given two properties to you. Number one, the first property is they diverge radially outward. They diverge radially outward from a positive charge, isolated positive charge. Had there been no other charge around it, the electric field lines would diverge out radially. And if there is an isolated negative charge, no other charge around it, only this negative charge, the electric field lines will converge towards this negative charge. So these are the two properties. So the third property can be written in a combined manner. Had there been a positive and a negative charge, what would happen? The electric field lines, they will emerge from positive charge and they will converge towards negative charge. Now think of a situation where these positive and negative charges are not isolated, rather they are placed quite close to each other. What will happen if they are placed quite close to each other? Think of the situation. Think of this situation. I have got a positive charge, I have got a negative charge. What would be the electric field lines would be? If I keep a positive charge over here, the positive test charge, it will move away from it, it will move away from it, it will move away from it, no doubt about that. But what about the charge? What about if I place the test charge over here? It was trying to move away, but suddenly it came under the effect of negative charge. And what will happen? It will converge towards the negative charge. Similarly, if I place a positive charge over here, it will go like this, and it will go like this, it will go like this, it will go like this, and more lines for negative charge can be drawn. Now this is the situation when a positive and a negative charge are placed quite close to each other. The electric field lines would be something like this. You can draw more of them. Imagine that if you place it somewhere over here, what will happen? It will go out there. Now as it is going, its distance from positive charge is increasing, but if I point it like this, the relative distance from the negative charge is not increasing as fast as it is increasing from the positive charge. So what will happen? The effect of negative will go on increasing, and at some point it will attract it backwards towards the negative charge. So this is the situation for a positive and a negative charge. What will happen if two similar charges are placed close to each other? In this case, you may also think of the situation as if the electric lines due to two dissimilar charges, they attract each other longitudinally. The lines were going like this, the lines were going like this, and they just simply attract each other longitudinally. Longitudinally means along their length. They just merge into one another. Now what will be the situation if I keep two similar charges close to each other? What would be the pattern of electric field lines? the situation would not be quite different if I keep both of them as negative. So I'm just taking one case that both of them are positive. Now what will happen? No problem about these lines. You can imagine if I keep a positive charge over here, in which direction will it go? Obviously in this direction it will go. Similarly, the situation is identical for the other charge as well. But what will happen if I keep a positive charge over here? It tends to move away from it, but at a point where, as it is moving from charge 1 to charge 2, what is happening? The effect of charge 1 is decreasing, but the effect of charge 2 starts to increase. At some point of time, the electric field will become zero actually. We have calculated earlier in some lecture how to calculate where the electric field will be zero. At that point, there will be no electric line. It will try to escape from the repulsion of this charge and move in this direction. Similarly, it will go like this. Somewhere over here, there is no electric field. So this point is probably, you can very well say, is the point where electric field is zero. Sometimes you call it neutral point. No issue. But you can practically think of the situation that what's happening out there. So it seems when there are two similar charges, it seems as if the electric lines, they are trying to push each other away. We call this lateral pressure. The electric lines are putting lateral pressure on each other. Lateral means sideways. They are putting lateral pressure on each other. If there are two similar charges, the electric lines put a lateral pressure on each other. Now, let's think of a situation when the source of charge is at infinite distance away. Earlier we are thinking of these charges when charges are assumed to be point charges. Now what is happening? The electric lines are like this. You can think that electric field is stronger over here and electric field is weaker over here. Electric field is weak and strong at this point. Weak at this point, strong at this point. You can think that electric lines are quite close to each other, where the electric field is strong, and as the lines they go far away from each other, the field goes on becoming lesser and lesser in magnitude. Now you can think of it when the charges are at infinity and the lines are coming from infinity. I've got some sheet. There are so many charges. This is one way of thinking of it, that electric lines are parallel. You can think of the situation when either the charge is at quite far away, you can get parallel field lines, or you can think of a situation where there are number of charges, infinite sheet of charge, and then even then you can get a uniform electric field. Now in this case, even if I look at different points 1, 2, 3, 4, 5, at all points the distance between electric field lines is identical. That means electric field is neither increasing nor decreasing in magnitude. This type of electric field is what we call as uniform electric field. And we simply represent it by closely spaced crowded lines if the field is strong, and widely spaced lines if field is weak. This is another property. That when you have got crowded electric field lines, that refers to a stronger field, electric field region, and when they are widely spaced, that refers to a weaker electric field. Now there are more properties. For example, you can extend these properties. There cannot be a limited set of properties that these are the only properties. This is not like that. This is the behavior of charges and being represented in terms of these electric lines. And what you can do, you can have n number of new properties devised. I'm just telling you what kind of these properties are and what's the origin of these properties. Let's come back to that a pair of dissimilar charges. One is positive, the other is negative. Now I placed a test charge over here. In which direction did it move? It moved like this. So let's say this charge is someone whom I can talk to. I asked him, in which direction you are going? He said, I am moving in this direction. Sometime later, the charge reached at this point. I again asked him, in which direction are you moving? He said, I am moving in this direction. Later on, it started to move towards the negative charge. And I again asked him, in which direction are you moving? He said, I am moving in this direction. That means that when a test charge was moving in the region of electric field produced by a number of different charges, it may change its direction. It may change its instantaneous direction of motion can be different at different points of time, at different points in space as well. Then the new property, the next property of electric lines comes into the picture. I would say electric line represents a path such that the tangent to electric field, tangent to field line at any point represents the instantaneous direction of motion of the test charge. I repeat, the tangent to electric field line at any point represents the instantaneous direction of motion of that test charge. Instantaneous means at that instant. At that instant, it's moving in this direction. At next instant, it's moving in some other direction. So at any instant, if you have got an electric field line given to you and you wish to know in which direction the test charge is moving when it is at a particular point on that line, simply draw a tangent to that. That tangent will give you the direction of instantaneous direction of motion of that test charge. Now, think of one more very important property, that two electric lines will never ever intersect. Two electric field lines will never ever intersect. Can you prove that? It's quite easy. Just assume that what I am saying is wrong, that electric field lines never intersect. Let's say they do intersect at some point. Now use the previous property, that instantaneous direction of motion is given by the tangent to the electric field lines. That means at this point I can draw one tangent and I can draw second tangent, because there are two curves. If there are two curves, I can draw two tangents. That means when test charge is over here, test charge comes over here, it has got two instantaneous direction of motion. One test charge at one point of time, at one point in space, will move only in one direction. It cannot move simultaneously in two different directions. That means our supposition is wrong. The test charge cannot move in two directions, 1 and 2. It cannot move in two directions. That means there cannot be two tangents. And that means there can be no point of intersection of two electric field lines. I hope it is clear to you. So these are a few properties of electric field lines. And now there is a small assignment for you. Can you draw neutral points? I have already drawn neutral point. I have already told you about the concept of neutral point. When two similar charges were there, you have mathematically calculated the position of the neutral charges earlier in numericals, and now you know theoretically what's happening out there. Can you do it? Can you draw the position of neutral points for two dissimilar charges of different magnitude and then for same magnitude? I leave it as an assignment for you. I know you are very much capable of doing it. In the next part, we will be covering some topics related to electric field produced by a dipole and some other cases. And then again, you will find the analogy between the numericals of electric field and the numericals of force due to the Coulombian force which we were doing earlier. Now these analogies you will find out that doing one kind of numerical, the other kind of numericals can automatically be solved. So that's why I had limited my discussion on numericals earlier, and I have covered the electric field now. After a few theory topics, we'll again come back to the numericals of not only of electric field, but again back to that which can be solved in a similar way for force, in the Coulombian force, for a distribution of charges. I hope these lectures are useful to you. If these are useful to you, do share them. Thank you.